The title of this course is Linear Algebra: Foundations to Frontiers. What we would like to do is already give you a glimpse at the frontier in this first week. The frontier we're going to show you is how we, as part of our FLAME project here at the University of Texas, encode algorithms in code. Now, our philosophy is that the algorithm should be expressed in code as much as possible in a way that reflects how one thinks about the problem. So, in the last unit, we showed how to think about the algorithm in terms of subvectors. What we're now going to show you is how to represent that in code in terms of subvectors. Let's have a look. So we're going to discuss how to translate an algorithm expressed with what we call FLAME notation into code for MATLAB. What I have here on the screen on the left is the dot product routine expressed using FLAME notation as found in section 1.6.2. Now, how are we going to do this? Well, we code in a very strange way. There is a link to a web page that you can find in problem 1.6.3.1 that will pop up a web page that we call the Spark web page, and we're going to use it to generate a lot of the code that's going to implement this dot product. And what do? Well, you fill out the menu on the left, and as you fill out the menu on the left, on the right, MATLAB code will start appearing. So we start with a function name. We'll call it dot. So here we filled out dot, and what we now have is a dot function. We want this to be an unblocked algorithm. What the difference between a blocked and an unblocked algorithm is will become clear later in the semester. So now notice that the function name is dot_unb, which stands for unblocked. Often there are different algorithmic variants, different algorithms that one can implement for the same operation, in which case you may want to pick a variant number. Let's just leave the variant number empty or none, and let's move on to the operands. Now on the left here you notice that the dot product requires vectors x and y and output alpha. That's 1, 2, 3 operands that we're going to pass to this particular function. So the number of operands is 3. Now the first variable we're going to call alpha, and notice that alpha indicates that it is actually a scalar. So we're going to say that a is actually a scalar, and notice that over here now the a has been replaced by an alpha, and alpha is both input and output, and that's just a convention that we're going to work with. Let's not elaborate on that. And then we need a vector x, which is a vector through which you're going to march from top to bottom, and it is input. And then we have a vector y that also we're going to march through from top to bottom, and it is input. And then we have different programming languages that we can choose as output, and we're going to stick with FlameMATLAB because that is our FLAME API for MATLAB. If you want, you could go and fill in your name, in which case that would appear up here in the comments. And obviously it's a little bit annoying that we get this copyright notice here. You are free to ignore that. Okay, so let's move this over a little bit and let's stare at this. What do we have now? Here it says algorithm to compute alpha defined as dot of x and y. Here we have a function that takes as input alpha x and y and as output gives alpha out. Over on the left we have x being partitioned into a top part and a bottom part. On the right there is a function that we have that takes the vector x, that partitions off the top part, and the top part is indicated to initially have 0 elements. That captures what we have here on the left. creating a top part and a bottom part. Same thing for y. Then we say, while the number of elements in the top part of x is less than the number of elements of x, over here we examine the first size of array x top and compare that to the first dimension of x. And as long as those are not equal, you stay in the loop. Okay. Then we say, let's repartition the top part and the bottom part of x into x0, chi1, which is the first element of the bottom part of x, and the rest of x bottom. Over on the right, we take x top and x bottom. We say partition off one element off of the bottom part of this vector, creating x0, chi1, and x2. Same thing for y. So that's how it captures the repartition. At the bottom we have to continue with by moving that one element across the thick line, adding chi1 to the top part of x, and for that we have a function down here that says add chi1 to the top part of x. Same thing for y, and then in the end we output alpha. So the only thing that this web page does not automatically create for you is how alpha needs to be updated every time you go through the loop. So what you do is you select all, you copy it, you go to MATLAB, you say new function, and you copy and paste this into the new function. Let's get rid of this annoying copyright notice. And what we now have is most of what we need to implement this routine. Move this over a little bit. Let's move this over a little bit so we can see it. The only thing we now need to do is to update alpha as part of the loop. So we highlight all of this, we erase it, and we say alpha should be updated by multiplying chi1 times psi1 and add that to alpha. We then save this as dot_onBlock. And now we can bring the command window back up. We can create two vectors. We can create a scalar alpha. And what we end up implementing, there's one thing we forgot to do, and that is to set alpha equal to 0 up on top. So we need to go back to this particular routine and say, okay, before we start the while loop, we should set alpha equal to 0. Let's save it again. Now we only set alpha here equal to 0 because we need to have a scalar alpha to pass into the routine. What we then do is we say, okay, we can set, let's take the output to be beta. Let's set beta equal to, let's see, we call the dot unblocked of alpha comma x comma y. And it tells us that the dot product of x and y is 5. Let's check that. X transpose times y, which is another way of doing the dot product, is indeed 5. Welcome to the wonderful world of how we program in the Flame Group. What we actually do is we code in C, and we've actually written libraries that have hundreds of thousands of lines of code this way. These codes are highly reliable because it's very difficult to make errors the way we code. And they actually tend to also achieve very high performance, and how they achieve high performance we'll talk about later in this course.